Now I start then with prenormal science, okay, according to this program. I start with a phase of prenormal science and then tell you what's coming next, the transition then to normal science, and that's the way I developed this model. Now, prenormal science is a scientific practice which is not very structured and in which various schools compete. Just to give you an immediate example of what normal science is not, if you look at today's physics, say classical mechanics that you've learned, or classical electrostatics, there are not various schools who compete. It's just a consensus that people know how electrostatics works. It's Coulomb's law with everything that follows from it, right? There is no disconsensus. There is a consensus. There are not various schools. So it is something which you may know from other fields, but certainly not from today's, say, school physics that you learned in your university classes for your bachelor. So, but I'll give you an example. These different schools, you may know that from the social sciences. The social sciences are pretty much like this in many aspects, that you have various schools that compete, say in psychology or in sociology or political science. You have various schools. There's not just a general consensus. And it's similar to what is here called prenormal science, but I'll come back to this question. If you ask yourself what is the difference between these various schools, you'll get an example a little later, that they have fundamental viewpoints about their subject matter. So they're all dealing with a certain subject matter, but there is no consensus about the viewpoint, how you should look at that, and how you should conceptualize it. There are even disagreements about what does and what does not belong to the field. If you have a certain field of phenomena and you have different viewpoints, you may agree about certain phenomena that they belong to this field, but you may disagree about other phenomena, whether they belong to the field, right? There is even disagreement what belongs to the field and what does not belong to the field. Now, this is pretty abstract, so I give you an example from a phase of normal science, namely research on electricity in the first half of the 18th century. I know that you don't know anything about that, unless it's your hobby to do some history of science. Okay, but I just explained to you, and it will be plausible in a minute, that there are different schools with very different viewpoints. So in the first half of the 18th century, electricity was a phenomenon that was not understood. Right? People just had a few phenomena. They knew it's different from gravitation, it's something else, but they didn't understand very much. And you know the phenomena there of static electricity, you may remember, I hope at least from high school, if you have a glass rod and you rub it, and then you have little pieces of paper, then it may attract the pieces of paper. Right? This is static electricity, you may remember that. Right? Or you have different materials and then different things happen, and suddenly the things have not attraction, but they move away from each other, and you have these phenomena. These are described somehow by static electricity, right? By static in our modern terms, that somehow the little pieces then of paper or whatever, they have an electric charge, and therefore they attract each other, or they repel each other, right? But people didn't have the concept of electric charge in the early 18th century. They didn't know that. That was an invention that came later. Now, people saw these phenomena that I just very quickly described to you, and there were very different schools. And I'm describing you now the viewpoints of 3 different schools, such that you get a feeling for how these different viewpoints could look like. Electrostatic attraction, you know, that the things attract itself, or that electrostatic attraction and the frictional generation of electricity were seen as fundamental by one of the schools. You know, the frictional generation of electricity, that is when you rub your glass stick, say, on cat fur. That's sometimes used. It's very effective, right? You take the glass stick, you rub it on cat fur, and then you go to pieces of paper, and then it attracts the pieces of paper, right? That's the phenomenon. So people observed that and said, okay, the fundamental phenomena for this Very strange. It wasn't called electricity at that time. For this very strange phenomena, the fundamental phenomena is the electrostatic attraction, namely that then the pieces of paper are attracted to the glass rod, for instance, and the frictional generation of electricity. Right? They thought this is fundamental. There is another phenomenon, namely the phenomenon of electrostatic repulsion. Right? The two things with the same, as we describe it, with the same charge, repel each other. Right? And people thought that's not a fundamental phenomenon of electricity. They didn't know. For us, of course, we know attraction is as good as repulsion because it's the same sort of phenomenon, because we have two different sorts of charges. But two different sorts of charges was discovered much later. Right? That wasn't in the beginning. In the beginning, people just saw the phenomena, right? They saw the glass rod, and then the pieces of paper. Of course, they didn't use our paper because they didn't have that sort of paper, but little particles, whatever they were, and they were dancing around, and there was attraction, repulsion, and one school decided, well, the fundamental phenomena for electricity that have to be explained somehow is really this electrostatic attraction and the frictional generation of electricity. This is the goal. And the other one, that from time to time you also have this repulsion. People thought, that's not important, right? That's not fundamental. But what's really fundamental, you take the rod, you rub it, and then you get this attraction, and that's it. That's the main phenomenon. Now, this is, of course, quite a legitimate point of view if you don't know anything else, but these phenomena, you say, look, these are the fundamental phenomena that I observe. There is something else sometimes going on, but that's not fundamental, right? It's a side effect of sorts, and we don't understand it really, okay? That's one of the schools. Now, here's a different school. The other school said, no, attraction and repulsion are equally fundamental. So, if we want to understand electricity, we have at the same time to understand attraction and repulsion. It's completely symmetrical. And that's, of course, a very different point of view, right? They don't concentrate on this rubbing. They say, whatever that rubbing is, this is, so to speak, a precondition, but it's not fundamental for the understanding of electricity. What's fundamental for the understanding of electricity is that we have both attraction and repulsion. And we must concentrate of getting this symmetry between attraction and repulsion, which is, of course, a very different point of view. Again, if you don't know much about electricity, that's equally legitimate. And you may say, yes, that's also an extremely good starting point. Or from our point of view, we'd say this is the better starting point than this one, because understanding the frictional generation of electricity is much harder than simply understanding what is the basic thing happening in electricity, namely attraction of unequal charges and unequal sign, and repulsion if they have equal sign. That's our theory today, but they didn't know that, right? So Antia was a third school. They didn't really care very much about attraction and repulsion, but they had discovered the phenomenon of conduction, currents. And they said, look, all this attraction and repulsion business and also this frictional generation is fine, but it's not at the center of what electricity is. And they worked with an analogy, or not even, no, it's not an analogy. They believed electricity is a fluid, literally a fluid, like water, right? And they said, that's the fundamental thing. We discovered with these phenomena a certain fluid. And what we have to understand is the properties of that fluid. And that's the fundamental aim of electricity research. This other stuff, attraction and repulsion, will come later. That's not our point of view. But the point of view is we've discovered a new fluid, and if we want to understand this fluid, we must know the properties of that fluid, which is, of course, again, a very different point of view. And that is the characteristic situation in pre-normal science, that you have certain phenomena, and you start developing a certain viewpoint about, for instance, the importance of phenomena, and about the fundamentality of certain ideas. And there you may differ wildly, right? Really deep differences. And it's very difficult if you look at that, and if you look at the phenomena that were known, that I quickly described to you, it's very difficult to make a decision here. What is the right point of view? They can't be all right somehow, they're different. And it was these schools that were competing in this phase of pre-normal science that I describe abstractly in the following way: a scientific practice which is not very structured, in which various schools compete. It is not very structured in the sense that these people do very different things. They follow very different lines of thought. They're developing very different sorts of experiments. If you say, in this school, you do not develop special experiments in order to study repulsion. Because you say, no, wait, repulsion is a secondary effect. That's not that important. We don't want to study this. We want to study, for instance, more precisely, the connection between the frictional generation of electricity and electrostatic attraction. That is fundamental, right? This must be our main focus. And don't develop experiments that tell you more about electrostatic repulsion. It would be a diversion. It would lead nowhere, right? Because it's not fundamental. And we must first understand the fundamental stuff. Whereas these people from the third school here, they will develop experiments and think about that. How can we discover more and know more about the properties of that strange fluid? For instance, does this fluid have a weight? Right? How heavy is it? That would be, of course, a question that's quite natural for them to ask about the weight of this electric fluid. Whereas the question of the weight of an electric fluid for these people doesn't exist at all. They wouldn't understand it. They say, what are you talking about? A fluid? I'm sorry. What we see is attraction and repulsion, and the point is understanding why is there both attraction and repulsion, and they have the same level of fundamentality, right? Again, in contrast with this school that says, no, wait a minute, no. You must understand this friction business of generating electricity. That's fundamental for an understanding of electricity. So that's a very typical example, therefore I choose it, of course, to get acquainted with that phase of pre-normal science, where you have these different schools with these different points of view. And as I said, they are completely legitimate if you think about it. If you just know these phenomena and you start thinking about a deeper law behind this phenomena, a deeper understanding of these phenomena, of course these three different viewpoints are all plausible. And if you say, okay, I find this one most attractive, so I do my research here, and therefore I will make investigations in attraction and repulsion and compare the two and look at them, have they equal strength or different strength or whatever you do then, then you are on a research trajectory, on a research program that is of course different from these. And therefore the whole field of electrical research is somehow structured into different schools. And these people ask different questions and make different experiments and may even disagree whether a certain phenomenon belongs to electricity or does not belong to electricity. Right? And this is, of course, a very difficult situation for them to communicate and make progress here. Now, that is how most of the sciences we know of have started. The only field where we don't really know that phase is astronomy, because it's so old. In astronomy, we don't know the phase of pre-normal science, because everything we know from the sources in astronomy is that people did have already a certain understanding and a certain consensus, say in ancient Greece, or in the other cultures. There seems to have been a certain consensus, and we don't know what the phase looked like in astronomy. But in the other natural sciences like chemistry or in all different fields of physics, we know of these pre-normal phases which have these characteristics of these different schools talking, having different points of view. Okay. So that looks, in a sense, a little less than science, real science, because in real science, what we are used to say in physics is, of course, that, or engineering, we have a consensus, right, about the fundamentals. If you look at engineering disciplines, there's typically a basic consensus. There are differences concerning smaller things, but certainly there is a basic consensus about what the field is and what the problems are and what the fundamental theories are. But that's not the case, and of course you can imagine that if you have a field with a consensus, that when you go back, that the consensus wasn't there from the very beginning, because this consensus had to be formed. And the phase before the consensus, that is pre-normal science. Okay? So, let me see whether I can continue from here. Mechanically, I can. All right. Okay, is this clear and plausible, this form of prenormal science? It must be plausible, you know, it can't be more because I only give you one example. Now the question is, how come, or how can it possibly be happening that people move out of this competition of schools? And that is the transition to normal science, what is called normal science, of which you don't know yet what it is exactly. And first I give you a name. The transition to normal science is called the maturation of the field. It becomes mature. Mature in the sense not like an apple, well, also like an apple that it's, you know, has a full form then, or a mature biological item, meaning it has then all the capabilities that usually connected with that specific form of life. In this particular case, the maturity of a science means that it resembles what we usually think, today at least, what a developed basic natural science looks like. And a fundamental characteristic of a basic natural science that has become mature is that there is a sort of consensus among the specialists, right? That's different from the social sciences, because in the social sciences, even among the specialists, there are typically differences about fundamental questions. But in the natural sciences, they are somehow different, and therefore also sometimes a model for the social sciences. A characteristic point is that, not always, but sometimes the practitioners of a natural science, of a specific field, have a certain consensus, right? They agree on the fundamentals of the field. And that is a characteristic of normal science, to which I come back in great detail. But here we look first at the transition. We have in pre-normal science different schools. They are in competition. There are different viewpoints. And now we get a sort of a transition phase called the maturation to normal science, and we have to look how that can happen. Now, the source of this maturation, of this leaving the stage of pre-normal science, is that one of the schools produces an extraordinary convincing solution to some of the fundamental problems of the field, such that the members of the other schools join this school. Okay? We have these different schools, say, of electricity, and they deal with the problems of electricity, trying to understand attraction and repulsion and the generation, frictional generation of electricity. And now imagine the following thing, that these people know about these different phenomena, and now one of the schools develops a solution that is extremely convincing, such that people get the feeling, oh, we in this school have solved one of the fundamental problems of the field. And the people from the other schools observing that then say, oh, they have a fundamental solution, we don't. Why don't we join the others? Right? It is just by developing such an extraordinarily convincing solution to some of the fundamental problems that the members of the other schools say, look, there are much more chances in this school than in our school. We didn't move much, right? We didn't solve any of the fundamental problems, but they did. I think their school is the better one. Why don't we join them? Okay? That is what historically has happened again and again and again, right? From this pre-normal phase with these competing schools, sometimes it took a very long time, sometimes it didn't take such a long time, maybe a few decades. Well, a few decades, quite a long time if you look at your own life. But it may happen then that one of the schools is really so successful such that the other schools join that school. The fundamentality or the extraordinary character or the convincing character of this solution must be such that the fundamentals of the field now seem to be clear, such that further research can be built upon them. That's the idea. So it's not just a very nice solution to a problem and then you say, finish, okay, where do we go next? No, it's a fundamental solution such that you think, oh, we can build further research on that. We can continue from here, and we have an avenue of further research. We can hope that we can develop interesting problems on that basis, right? So it's a promise for fruitful further research, and that's most important. That's why it's interesting to join the school. It's not interesting to join the school because they were so good in the past, right? That doesn't help you for your career, for your future as a scientist. But the point is there must be a strong promise of good research, fruitful research, where you can excel and show your abilities and capabilities of doing research, and that's the promise of this extraordinary solution. The fundamentals now seem to be clear, and further research can be built upon them, and that makes the attractiveness of that what happens in this school. Again, you may say, well, why should that happen? Well, I can't tell you really, but I can tell you that in the history of science, that is what happened again and again. And that is how modern science formed, that out of these phases of pre-normal science, one of these schools typically, after a while, short or long, they found a solution to some of the fundamental problems with exactly these characteristics, extremely attractive for the other schools, such that the members of the other schools then came to this school. Now, when I say that the solution was extraordinary and attractive, that means an evaluation. I'm using values. I'm not just describing what the details were, but I'm saying I'm evaluating it as especially positive, right? I'm saying it's attractive. And you can, whenever you say something is attractive, or you value it as good, attractive, or extraordinary, there are certain values in place, okay? So if you value a certain university as especially good, then you have certain values. For instance, you value research as very important, or teaching especially important, or especially courses, say in horticulture science is especially good or important. And then you choose it, right, on the basis of values. Or if you find a certain partner of the other sex or of the same sex, whatever your preferences are, if you find him or her especially attractive, you value certain things. She is especially beautiful, or she's especially rich, or she's got especially nice hair, or whatever it is. You have values. You're applying values. Or beautiful eyes, or whatever it is, right? But you're applying values. Whenever you make such choices, you're applying values. And why I'm saying this? Well, for entertainment only. No, not for entertainment only, but in order to apply that here. So when people say this solution of this school is extraordinary, attractive, the question may be on the basis of which values? What is the basis from which they evaluate this as especially attractive? And here what we have in scientific humanities is so-called scientific values. And that means here the decision for a theory associated with the outstanding solution is based on a set of scientific values. And the scientific values that are relevant here, I'm giving you some sort of, not a finite, not a definite description, but I'm just hinting at some of these values. They include scope, accuracy, predictive power, consistency, and fruitfulness. And I'll tell you a little more what these values mean. Okay, remember, the one school develops a solution to fundamental problems, and this solution is always connected with some theoretical elements. Say, for instance, yes, electricity is a fluid with such and such properties, and therefore we can explain a broad range of electrical phenomena. Now, the scope of a theory means the range of possible applications. And the more possible applications you have, the better a theory is, because it's more useful. You can do more predictions, you can do more explanations, because you can apply it to more and more phenomena. So one of the aspects what makes a theory attractive is not the color of its hair, because theories usually don't have hair, but they have scope, you know, the scope of possible applications. And that is something you look at when you have a choice between theories. This one is a very narrow theory, only covers very few phenomena, and the other one covers many phenomena, so you take that one that has a broad scope. Another one is, of course, the accuracy, the quantitative accuracy, for instance, of the predictions. If a theory that predicts more accurate, of course, it's a better theory. Or if it explains more accurately, of course, it's a better theory. Another one is here predictive power. A theory that has more predictive power, can predict more phenomena, is of course a better theory. That's what you want from theories. They should predict, as I told you in the first or second session. And the consistency, a theory that's consistent, right, where all the parts somehow cohere and are consistent with each other, is much nicer than a theory that consists of different parts without connections or even in contradiction. And you just say, yeah, I have to use it, I'm sorry, it's not consistent, but that's the best I have. So you prefer a theory that's consistent. And that's a more general, again, description, a theory that's more fruitful, meaning in directing your future research, what you should do next, is of course a better theory than a theory that's less fruitful. So these are the values, and they are very important, quite apart from paradigm theory. The scientific values, these are the typical scientific values by which scientists, and that includes us as well, by which scientists evaluate theories, right? These are the values that are used here: scope, accuracy, predictive power, consistency, and fruitfulness, mainly. And they form the basis on which the accomplishment of one of the schools, this extraordinary convincing solutions, is judged. That's the basis for the judgment, right? So it's completely transparent what's happening there. I mean, the scientists run around with these values and they say, we look for a theory that has these properties: broad scope, accurate, predictive power, consistency, and it's got to be very fruitful. And then one school develops a certain solution for a fundamental problem, and they say, here's our theory that's connected with it, and then you look at the theory, and then you discover it's much more broad, it's much broader, more accurate, has more predictive power, and so on and so forth, than the competitors, and then you say that's the better theory. That's what I'm going to work with, especially because of this one here, of the fruitfulness. Because as a scientist, you want to work with a theory, right? That's the whole idea of it. You want to work with a theory and do something with it, develop it, apply it, whatever it is, and therefore you look for theories that are as fruitful as possible. That's your whole job as a scientist, right? Therefore, it's completely transparent why scientists then leave their own school and join the other school that developed a theory with these properties and that is able to solve one of the fundamental problems of the field. That's then convincing, and then people start to join that school. And then you'll see they will, in the end of that process, they belong more or less to the same school. Okay? I'll give you an example. It's something happening in the beginning of the 20th century, namely it's the victory of Bohr's atomic model. Right? Bohr's atomic model, this so-called planetary model, where you have a nucleus, a small nucleus, positively charged, and the electrons traveling around it in sort of circles. And in order to show you, this was in atomic theory really the first phase of normal science, and I tell you a little about it, which is of course then quite plausible because you are familiar with the fundamentals of atoms. A certain consensus that atoms exist was only reached in the end of the 19th century. Before, there were different viewpoints. You know, some people thought that atoms exist. Other people did not believe in the existence of atoms. At the beginning of the 20th century, most people believed in the existence of atoms. They said, yes, matter is not continuous, completely continuous, but matter is corpuscular, right? There are somehow small particles like the Greek atoms. The atoms is an invention by the Greeks. It's something which you cannot divide. That's the literal translation of atoms, something which cannot be divided. And the basic idea was, yes, matter has a corpuscular structure. There is something like atoms, you know, units, small units, and all matter is composed of these small units. The question is, what is the nature of these small units, right? What is it? What people knew in the beginning of the 20th century was that in these small units, there are positive charges and negative charges, right? And that was a development, of course, having begun much earlier. It was a discovery in the 18th century that there are two sorts of electricity, right? Negative and positive. It was a very deep invention that gave an explosion of results, because once you order the electric phenomena by means of positive and negative charges, which is a completely new idea, then you get a very powerful theory, and it's so powerful that still today, of course, we believe in electricity that there are positive and negative charges. It's part of the most fundamental models in physics. The Standard Model, of course, works with positive and negative charges, electricity. Okay, so it was known that there are negative and positive charges somehow in the atom, but people didn't know what the structure of the atom was. And one very popular idea of the atom was that the atom is some sort like a cake, right? A continuous cake that is positively charged, and in that cake, like raisins, there are small pieces of negative charge, right, in between, right? The whole thing is neutral then, if that has, say, the cake stuff, the continuous positive charge, say, is 4, and then these little spots have then a charge 1, -1, then the whole thing is neutral. And that was the basic idea, that somehow that's a unit, some sort of sphere, you know, positively charged, and in between are these little spots like raisins in a cake. Therefore, it was also called the raisin cake model of the atom, where these negative charges. Now there was a guy in England, in Britain, Ernest Rutherford, and you may have heard his name, who was a very famous experimentalist. And what he could show is that this model is false. That doesn't really work. And what he did is he sent electrons to the atoms, and what he found is that most of the time the electrons go through the atom, and in some exceptional cases, which were extremely surprising, the electrons came back. Right? And that, he said, somehow the structure of the atom must be different. It must be such that the atom itself there is something in the center that's positively charged, and then there is much empty space, and somewhere there must be something negative, but he didn't know how, you know, from the experiments. He said mostly an atom is empty space, which was a real big surprise. But in the center, somehow there is a positive charge such that if an electron comes straight to the center, it's repelled and comes back. So people were quite surprised. Most of the electrons that were sent to some piece of, say, a sheet of gold or something, most of the electrons went straight through, but a few came back. They said that's very, very strange. So that were the empirical data that were known. People knew there were atoms. This was also the experience of chemistry that was strongly suggesting that there were discrete units. It was not just homogeneous and continuous. Matter was just somehow built up of atoms. But the problem was, what is the structure of the atom? The problem here is from electrodynamics, that you know that this can't work in a sense. This model that in the center there is a positive charge, and somehow around it are the negative charges. This can't work, this can't be true from the point of view of electrodynamics. Why? Because these charges go immediately to the center and the whole damn thing collapses, right? So there is no way that we have stability such that there is a vacuum, so to speak, within the atom. There is just no way. Why not? Well, because the negative charges are attracted to the positive charges, and the empty space here won't be stable. So matter will always collapse. And of course, it's one of the most fundamental aspects of matter that it is stable, that it does not collapse. So it was a big mystery by these experimental results that most space occupied by an atom is really empty space. It was completely incomprehensible how this empty space could survive in atoms. People didn't understand that at all. So here comes, in 1913, a young, completely unknown guy from Denmark. And Denmark was certainly not in Europe the center of theoretical physics. It was just a small country, you know, and there were a few Danes sitting around, and a completely unknown guy named Niels Bohr. And Niels Bohr developed a model of the atom that had extremely surprising properties. It was not fully understood at that time, but the Bohr model of the atom was extremely surprising, such surprising in 1913 that people did not believe it in 1913 and not even in 1914. People did not believe it. They said, that's a sort of funny game, what he's doing, but it's not real physics. So they didn't really believe it. But what Bohr's model did, it was first a description of the positive and negative charges. So the Bohr model is the following, that it says, if you have an atom as a whole, then there is a very, very small core, a nucleus, and that is positively charged. That's in the center. And then there is much empty space, right, vacuum, and around this are circling the electrons, right? They are circling around here, around the nucleus. And there's a distance here, or this one here to this one here is 10 to 5, 10 to the 5. So if we have an atom, say, of size 1, then the center, the nucleus in the center of the atom is extremely small. It's just 10 to the minus 5. It's very small. So most of it is empty space. So people, of course, saying, well, that's not stable, right? If you have electrons, if they sit here statically, they run immediately to the center. They are attracted to the center. And if they are cycling around here, that's not possible either, because electrodynamics then tells you an electron that's cycling loses energy, right? It radiates. An electron that has a curve radiates. That is a result of classical electrodynamics. So it loses energy. Losing energy means it becomes slower, and it's circling into the center. So the atom isn't stable. That was the first step. If you have a distribution of charges, distribution of positive and negative charges in that way, that you have a positively charged center and you have electrons trying to circle it, the immediate answer from classical physics is that won't work because the atom isn't stable. And one of the, as I said, one of the fundamental properties of matter is that it is stable. Right? It doesn't collapse within 10 to the minus 5 seconds. It is stable. It survives for years and decades and centuries and everything. So that was the first step, but that first step, of course, must be supplemented by something. Well, what Bohr postulated, and it was really a postulate that one did not really understand, and therefore it was also refuted by many people, he said, well, that doesn't happen. Doesn't happen. No. The orbits of the electrons are stable, period. Right? Please swallow that. That was the message. I don't understand it, but I can tell you my model of the atom is such that we have a positively charged center of the atom, and then we have stable orbits for the electrons. They can do that, and it's stable. Right? I know it's in contradiction to classical physics, but that's the postulates, and atoms just work that way, period. Right? People had to swallow that. That was part of it. Now, this has, of course, a wonderful consequence, and this is why Bohr had introduced it. You get the discrete emission spectra of atoms, and that's the following. You may know that if you have a gas in a container, right, and you heat the gas, then it starts to radiate, and the radiation that comes out, say it's light, and then you send the light to a prisma, and then you get the spectrum. And the spectrum is not a continuous spectrum, but you get emission lines, right? You get certain characteristic emission lines. That's called the discrete spectra. So if you have light from a gas, say, from hydrogen or whatever it is, and you analyze the light that comes out, that is generated through heating, you get discrete spectra, discrete wavelengths. So you've got lambda 1 here, and here different lambda 2, and here lambda 3. These discrete spectra were known, and they were very important in astronomy because you could identify the elements, right? You had a certain spectrum, and then you could say that spectrum belongs to a certain element. So the question was, say, if you've got H2 here, hydrogen, and you heat it, and you get an emission spectrum, the general idea was that from the structure of the atom, we must be able to understand in principle, first of all, why we have discrete emission spectra, right? That was the first step. And the second one was, why has hydrogen this spectrum and helium another spectrum and whatever element you take, again another spectrum, right? Not only that the spectrum is discontinuous, but also where exactly the lines were. And Bohr's model was the first model, as I said. The spectra, these regularities about the spectra were well known since the 1870s, 1860s, when people started spectroscopy, and it was a very important instrument in astronomy because then you could describe what elements were in the sun, for instance, right, and in the stars, which was an immense discovery in astronomy, that's spectroscopy. So one knew one knew the rules, and also there were certain laws about spectra that were well known. And the general question was, well, if these spectra are generated by the atoms, then somehow we should be able to understand the spectra, the specific line spectra emitted by a certain element. We should be able to understand them in terms of the structure of the atom, right? That was the idea. And that was Bohr was able to do. Bohr said, look, I can really tell you how spectra work. That's the following. What we have is we have different sort of stable orbits of the electrons around the nucleus. There are different possibilities. Not everything is allowed. Only certain orbits are allowed. For instance, one here, and then one here, and another one round here, right? Not all orbits are allowed. Only a few orbits are allowed. Okay? He could describe that. And he said, you know, what a spectrum is, or what the emission of light is simply, you have an electron sitting here, in which it has more energy than in the inside, and then what the electron does, it jumps from one orbit to the other orbit. And that energy difference here, that delta energy, that's responsible exactly for one particular line that's here. Because that's exactly the energy difference that you need, and then the energy is translated into a certain wavelength, and because we have discrete transitions from here to here, for instance, from here to here, or from here to here, different transitions. And all these transitions generate a particular line. So what you get is you get immediately by this model, by having these different shells, right, different allowed orbits for the electrons, by this simple rule that not all orbits are allowed, you get immediately, qualitatively, the line spectra. And also, if you fill in the details, how big the charge is, how big that charge is, how the energies here are, then you could calculate, indeed, the spectra. And the point was that Bohr could calculate already in 1913 the spectrum of hydrogen. And that was an incredible success, right? He was able, from his model, to use this model, apply the model to the hydrogen atom, using the mass here, using the mass of the core, the nucleus, using the mass of the electron, and using the charges here. And then he could derive from his model the line spectrum of hydrogen, right? This was predictive power and accuracy, right? The values that I mentioned here, scope, accuracy, predictive power. The thing was not consistent, right? Bohr's model is not consistent. But it is able to predict something that no one else could predict. All the other atomic models were completely unable to deduce the line spectrum qualitatively and also quantitatively to calculate the line spectrum of hydrogen. And that was an unbelievable success. It was said, but other people said, look, I value consistency very highly. And Bohr's model is not consistent. Why is it not consistent? It violates classical electrodynamics. It simply says, these orbits are stable. No explanation. Classical mechanics says, no, they're not stable. Right? Bohr says, yes, they are stable. Why did he say so? Well, he said, I know that matter is stable. Right? Somewhere the stability must come from. I don't understand the stability, so I postulate it. And he postulated the stability of the atom such that he got the line spectrum. Right? That he got the correct line spectrum by saying, yes, not everything is stable in the atom, but only a few of these, right? It's very specific. And he gave a rule how to calculate them, but you didn't understand the rule, really. But you could calculate then the stable orbits, and from the stable orbits you could calculate the line spectra, and the line spectra for hydrogen were correct, right? So this is an example where all other people who studied atoms and had different ideas of atoms, they could never ever compete with Bohr's model because Bohr could calculate the line spectra. And the line spectra, as I said, were known for decades, that be measured with extreme accuracies, very extremely important for astronomy and, of course, for chemistry. I mean, much of chemistry, chemical analysis even today is, of course, based on spectroscopy. You just heat the stuff and look at the spectrum and then you know what it is, right? It's wonderful. It's very easy. Physical method to describe to identify chemical elements and also compounds. So it was incredible what the model was able to do by calculating that. And then people said, look, this really solves some of our fundamental problems. It at least describes the stability of atoms. It doesn't really explain it, but stability of atoms is inbuilt in the model. And the stability of atoms, although we don't understand it really, therefore we are a little unhappy about it, we must accept, because what this delivers, this assumption of the stability here, what it delivers is the fundamental stability plus the line spectra, the discrete emission spectra. And no one else could do that. No other atomic model could do that. And then people said, that's the way to go, right? That model solved some of our fundamental questions about what atoms are, right? It does solve them. And what you get is, of course, the feeling, that's what I described there, you get the feeling that some of the fundamental problems are really solved and that it opens avenues for further research. Once you know that this is the structure of the atom, and you've calculated, say, for hydrogen, the spectrum, of course, the next step is to calculate the spectra for other atoms, for other sorts of atoms. So you had plenty of things to do. You could measure more spectra and then try to explain them on the basis of Bohr's model. So what you see, the fruitfulness for the future, not only for that particular case, hydrogen, but also the fruitfulness for further research, the scope, immense. Right, it's an immense scope when you know what an atom is, what the structure is. You can do many, many things, ask many, many questions, and answer many questions on the basis of this model. And that is what indeed happened then. It took 2 years, in fact, 1915, a very powerful physics group in Munich, around a famous theoretician, Arnold Sommerfeld. He started taking up the model. And because he was a giant in the field, he was highly respected, and he was first convinced, well, this model is somehow right. And they started there then calculating things, and then in a very short while, everyone else in atomic physics accepted Bohr's model. They said, that's exactly the right way to go. So it took, from the invention of the model from 1913, it took something like 2 years. And before, there were some 10 years or 15 years, people thought about atomic models. They had different schools. It was pre-normal science. Right, the cake model was one of them. This cake raisin model was one of them, and other models were around as well, ring models and complicated stuff. But and that model came then in 1913 as one additional model, and then people realized, oh, that's much, much better than anything else. Right? It's extraordinary. It's quite clear it solves the fundamental problems of the field. Of course, there are further questions. It doesn't say that's absolutely the end. We know everything now, because there was still this riddle about the stability of the orbits that one didn't understand really, but it was quite obvious that given the stability and its explanatory power for the spectra, that people thought there must be something in it, right? It must be somehow wrong, right. We don't fully understand it, but it must be somehow right, so they accepted the model. And as I said, Bohr's atomic model explains the stability of atoms. Well, I do scarce quotes here, because it doesn't really explain them. It builds stability into them, but in a very specific way. It just doesn't say, oh, atoms are stable, period. But it says very specifically what the stability of atoms consists in, namely in the choice that certain of these orbits are allowed. And they are stable, although classical electrodynamics tells you they are unstable. But Bohr says by postulating, no. Here are some specific things that are stable. And that's, of course, then, it's a sort of explanation. It's not really an explanation, but it's not a simple postulate that you simply, without any sort of specificity, say, oh, yes, atoms are stable, period. I don't understand it, but they are simply stable. No, he says much more. He says there is a very specific stability, namely specific orbits are stable and allowed, and anything else is unstable, right? When an electron would be here, no stability at all. It can't stay there. Right? It does something and moves somewhere. And from here to here, it's an almost instantaneous process where the atom moves from here. And it's a very precise distance here that is reflected then in very sharp spectral lines as they were observed. Okay. So this is a concrete example, and I hope you could follow the physics here. I guess you must be able to follow the physics. Also, the water engineers have enough atomic model and so on. Yes? A little plausible? Okay. Half plausible? Well, Google Bohr's atomic model, you can read more about it. It's a very, very interesting phase in the development of science. And I showed you that in order to illustrate what I mean when I say that the achievement that leads from pre-normal science to normal science may be such an extraordinary achievement based on these values, here, scope accuracy, and so on and so forth, by which you evaluate the model, in this case the Bohr model, and the evaluation is quite clear how you get the impression that this is the future way to go, and why this model is just very, very much better than any of the alternatives. And then if you worked, say, for 2 years on such a model, right, on the cake Raisin model, that you say, look, I did not get anywhere. I don't understand the stability of this thing here, right? Because why do the electric charges, the negative ones, stay inside the cake? Why should they do that? I mean, there's repulsion. They move away. So what keeps them there? You don't understand anything. Is there any way that from this cake model you can go to can explain the line spectra, the discrete line spectra? You don't see any way, right? No way. But then you look at Bohr's model and say, wow, it's just much more powerful, right? It's a way from which I can be sure if I use that model, it does not only explain H2, hydrogen, but it may explain other features of the elements as well. You may understand different things. And what one sees immediately, if you study that a little, that you get a handle on the periodic system of chemical elements, right? This was periodic system of chemical elements was known since the 19th century. People know that was in the second half of the 19th century it was discovered, and people knew there was this structure, you know, that 92 elements have a certain sort of periodicity in the periodic system of elements, and you could immediately see that you have a potential here from the atomic model to explain that, because you've got these different sorts of orbitals, and different numbers of electrons can be in one of these orbitals, and that is immediately a link to the periodic system in chemistry, which is also, of course, to be explained by an atomic model. If you believe in atoms, and we have different sorts of atoms corresponding to the different elements, chemical elements, then of course the laws that govern the chemical elements must be somehow derivable from the atoms, right? And you saw immediately when you see this model, you see immediately the potential to do that. And that's, by the way, that Bohr discovered on the basis of his atomic model. He discovered new elements. In 1921, he gave the Nobel speech in Stockholm, and he described the discovery of a new element based on Bohr's model, because he could calculate it and the chemist could find it. Right? So it was absolutely right that people then joining Bohr's model in 1915, that they saw correctly that it had great potential. And then between 1915 and, in fact, 1922, all the physicists working in atomic physics based their work on Bohr's atomic model. And this was a phase then of normal science. No competition between models. No competition between schools. Everyone knew that's the basis for physics. Atomic physics is built on Bohr's model, period. Right? No further discussion about that. And that is what we discuss further than in normal science. Once we have, by a triumph like this one of Bohr's model as one of the schools in competition with each other, once one of these schools has won, right, then a new sort of practice emerges. Because you don't have to look at competing schools any longer. There is just one school. And that's not a school, that's just physics then, in that particular, that's just atomic physics. So after 1950, this was atomic physics. Period. Atomic physics was done on the basis of Bohr's model. And this is then normal science that I described, the transition to normal science. And here is then the very, very first and preliminary description of what normal science is. Namely, normal science is a scientific practice that is characterized by a consensus of its practitioners about the fundamentals of the field. Right? And that is to be illustrated here with Bohr's model, that the fundamentals of the field, namely atomic physics, that is the structure of the atom, right? And everyone agreed, right? And that was a fundament, a real fundament for atomic physics, and it lasted, well, in that case, only 7 years, but still it was extremely fruitful research. Up to 1922, Bohr's atomic model was completely unchallenged, many problems worked, and I'll describe the practice of normal science a little later. And the point is simply that we have a consensus. That's the most important thing in comparison to this pre-normal phase where you have different schools. And you know, you may belong to one school, but you look at the other schools. Are they more successful than my school? Oh, I try to do here, but I'm not sure. It's a way of uncertainty, and that's just different from a science where you are sure you know what an atom is, right? And that was the case here with Bohr's model, okay?